And our final video of Chapter 7 is Video 5. And we're going to continue on with what we discussed in Video 4 with sampling distributions for sample means. But this time we're going to talk about what happens if the population is not approximately normal. Because in Video 4, our shape of our sampling distribution was all based on the notion that we've been told that the population standard or the population distribution is approximately normal. So I said we would save this for video 5 and talk about what if the population is either one, not approximately normal, or you just don't know what the shape of it is in general. So when the population is not normal or not known at all, the sampling distribution can be approximately normal if we have a large sample size. And the reason why a large sample size allows us to conclude that the sampling distribution is approximately normal is thanks to this thing called the central limit theorem. Now, the central limit theorem is really the central limit theorem is to statistics as the Pythagorean theorem is to geometry, let's say. The central limit theorem is one of the keystones of the foundations of statistics overall. Now, there's a lot to the central limit theorem. We're just going to talk about the real basics of what the central limit theorem does for us. And so here's what the central limit theorem looks like in action. A sampling distribution will act more and more like an approximately normal distribution as the sample size increases even when the population is not normally distributed. So we saw this back in video 1 when we first discussed the idea of a sampling distribution. And we started off with the population distribution that was related to rolling a single-sided die, and we could get a 1, 2, 3, 4, 5, or 6. It was a uniform distribution because they all had the same probability of happening. But then we started talking about what would happen if we took the means of multiple rolls of this die. And we started to notice the shape looked more and more approximately normalish. Now, even when we got to a sample size of 10, this thing really started to have that bell-shaped curve to it, but it's not perfect bell-shaped, which is fine. We would just need a larger sample size beyond 10 to really make this thing look truly approximately normal. Now, the thing is, how large of a sample size is needed for the sampling distribution to be close enough to approximately normal really depends on the shape of the population distribution. More observations are required if the shape of the population distribution is far from normal, if it is heavily skewed. But we can safely call the sampling distribution approximately normal once we get to a sample size around 30. Okay? Do not use the number 30 as any part of your explanation for any problem. Don't say, we can use the central limit theorem because the sample size is at least 30. What I want you to say in any type of problem where you have to justify using the central limit theorem why the sampling distribution is approximately normal is I just want you to say, we have a large enough sample size for the central limit theorem to apply. And that's how we know we are dealing with an approximately normal sampling distribution. So just know 30-ish is around that magic number, okay? Some textbooks say 30. Some say, well, not maybe 40 is a safer bet. Just know that once you're really beyond 30, you're pretty safe in assuming that the sampling distribution will be approximately normal, thanks to the CLT, the central limit theorem. Now, the one thing that people always mess up is they try to use the central limit theorem for any type of sampling distribution. But the central limit theorem only works with sampling distributions for sample means. Okay? Whenever we did sampling distributions for sample proportions, we had a specific rule. We had the n times p and the n times 1 minus p both had to be greater than or equal to 10 for us to conclude that the sampling distribution for sample proportions was approximately normal. So proportions have a specific rule for determining the approximately normal shape. But for means, we don't have proportions. So for means, we're going to have to try to use the central limit theorem in order to ensure that we know we're dealing with an approximately normal distribution. And here's our one example we're going to look at. It's split up into 3 parts. It says the number of lightning strikes on a square kilometer of open ground in a year has a mean of 6 and a standard deviation of 2.4. Notice here, they didn't give us any information about the shape of the population, so we can't assume that it's normal. The National Lightning Detection Network uses automatic sensors to watch for lightning in a random sample of 10 1 square kilometer plots of land. So you might be wondering here, we don't know the population's normal. We don't have a big enough sample size. You just told us we had to shoot for like a 30 sample size, and this is only 10. So the thing that we're going to conclude here is with this sampling distribution, we don't know what the shape is, okay? But what we can do in part A is we can go ahead and calculate a mean and a standard deviation, okay? We just won't know what the shape of this distribution is. So the mean of this distribution will be mu sub x bar is equal to the population mean, which is 6 strikes per year. And the standard deviation, sigma sub x bar, will be equal to the population standard deviation, sigma, divided by the square root of our sample size. So this ends up being approximately, oh here, let me backtrack here. This was equal to 2.4 divided by the square root of 10. And for sig figs, this is 0.7589. Now, we had a condition to be able to verify first that we can really calculate this standard error or this standard deviation of the statistic. And that was we had to check, is the population at least 10 times our sample size? This again is referred to the independent condition or the 10% condition. We cannot sample too much from our population, otherwise the math, the statistics, really doesn't work out the way that we need them to. All right, so who is our population? Well, based on our sample size of 10, we were testing 10 plots of land, right? 10 1 square kilometer plots of land. So really our population is all plots of 1 kilometer square land. And can we assume that there are more than 100 1 square kilometer plots of land? And that is absolutely, positively a safe thing to assume as being true. So we'll say assume true, and we're good. This standard deviation is legitimate. It is okay to calculate. Now, that's all there is for part A. So just know we've got a mean and a standard deviation, but we don't know the shape of the distribution. So part B leads us into that thing right there that we just talked about. It says explain why you cannot safely calculate the probability that the mean number of lightning strikes per square kilometer, x bar, is less than 5 based on a sample size of 10. So what we'd want to try to do is be able to calculate this probability using a normal distribution here, but we don't know that the sampling distribution is approximately normal. So in our explanation, I'm going to give 2 real reasons why we can't do this probability. So number 1, I'm going to state that we do not know if the population distribution is approximately normal, because if we did, then we could go ahead and calculate this probability. If the population is approximately normal, any sampling distribution, regardless of sample size, will also be approximately normal. But we just don't know if the population distribution is approximately normal. And then number 2, with a small sample size, you could mention of 10. I'm going to mention it. But if you just said with a small sample size, that would be fine. You don't have to specify how big it was. But with a small sample size of 10, we cannot use the central limit theorem, and it is absolutely okay to abbreviate the central limit theorem, the CLT. Okay, on the AP exam, they absolutely understand the CLT is the central limit theorem. So with a small sample size of 10, we cannot use the central limit theorem to guarantee the sampling distribution will be approximately normal. Now, if our sample size was more than 30, we could use the central limit theorem to guarantee the sampling distribution would be approximately normal. But we can't use the central limit theorem. All right? So there's part B. That's why we cannot calculate this probability. We can't use normal CDF or a normal distribution. So now part C says, suppose the NLDN takes a random sample of 50 square kilometers instead. Calculate the probability that the mean number of lightning strikes per square kilometer is less than 5. Well, now let's go ahead and discuss the SOX of this distribution. We'll go ahead and figure out the mean and standard deviation. The mean is still going to be 6, and the standard deviation is now going to be a little bit different. But we still get to use the 2.4, but now we got our enlarged sample size of 50, so I need to calculate a new standard deviation, which is 0.3394 to 4 sig figs. And once again, I would technically need to check the condition. Is the population at least 10 times the sample size? Well, now we're looking at all plots of land, really 1 square kilometer plots of land, but we'll just leave it as all plots of land. Are there at least 500 1 square kilometer plots of land? Yes, that is still absolutely true. So we've got a center, we got a spread, and now let's go back and talk about the shape. Because now with our very large sample size of 50, our sampling distribution will be approximately normal. So here's how we're going to have to write that part out. Okay, so with a large sample size, again, if you want to mention how large is, in this case 50, knock yourself out. So with a large sample size, the central limit theorem allows us to conclude the sampling distribution is approximately normal. So now we know the SOX of this distribution. Okay, we know it's approximately normal. We've got a mean of 6. We've got a standard deviation of 0.3394. So now to calculate the probability. What is the probability that we'd find a sample mean, an x bar, that is less than 5? And so we get to use normal CDF. Lower bound would be, technically 0 strikes, but if you want to put in negative 99999 or, say negative infinity, that's fine. I'm just going to put in 0 as the lower bound. Up to 5, mean of 6, standard deviation 0.3394. And so that comes out to be approximately 0.001608 to 4 sig figs. So we're talking about a little more than 0.1% chance happening here that the mean of 50 plots of land, would have less than 5 lightning strikes. Because really, we expect there to be a mean of, about 6. So just being less than 5 with such a large sample size, because our standard deviation starts to shrink dramatically here with our large sample size, it is a very rare occurrence that this would happen. Now, the one other thing I might illustrate is I've got a normal distribution. The mean, mu sub x bar, is 6. Now, 5, based on knowing what my answer is down here, I would find a sample mean of 5 really far down here, so that this is approximately 0.1%. Okay, so it really doesn't happen that often. And that is all for really chapter 7, unless you want to watch the bonus multiple choice video that is after this. Otherwise, we will see you in chapter 8.